In this video, I am going to draw on our learning from looking at the sign test as a randomization test and expand upon that to look at a randomization test with original scores. So if you have not yet watched the first video in this series, I encourage you to do so and then come back and learn about how we can conduct a randomization test with the original measurements that we obtain from our participants. You will note the subtitle, A Fisher Randomization Test, not the Fisher Randomization Test. Why is that? Ronald Fisher was one of the great statisticians of the early to mid-20th century, and he conceived of randomization tests in a general framework, not in terms of any one particular setting. In fact, he constructed some randomization test examples using a small number of observations, but never thought of it as practically feasible because he was working in a time without computers, and the computational power needed to do a randomization test will grow very quickly with an increased number of observations. So while he proposed randomization tests, he did so more as a thought experiment and in a more general framework. So we could call many randomization tests Fisher randomization tests, this one being the first, and the one that's the most simple once we get beyond the sign test. Some reminders from the sign test. There are 2 to the n possible sequences of plus and minus signs where n is the number of observations. If the median of differences between members of a matched pair are equal to 0, then each sequence is equally likely. That is, when the treatment is not effective, then each sequence of plus and minus signs is equally likely. The probability of a given sequence is therefore 1 over 2 to the n. In the previous video, I asked the question, if we randomize each member of a pair to the control and treatment condition and there is no treatment effect, what determines which member of the pair has the highest score? And we answered that it was chance that determined this, because one member of the pair has the highest score due to extraneous variables, not the treatment. Therefore, randomization determines if this person will end up in the control or treatment condition. You can view the scores obtained by the members of a matched pair as unrelated to the treatment, and therefore those are the scores that they would have obtained if you had not even had a treatment. And which one has the highest score just depends upon whether you happen to assign the person who would get the highest score into the treatment condition. And whether the individual in the treatment condition has the highest score only depends upon whether or not the person who was bound to get the highest score ended up by chance in the treatment condition. That reasoning is very crucial to the randomization tests we're going to look at right now. Here's the setup. We match participants into pairs based on extraneous variables. The pairs must be independent of each other. The members of each pair are randomly assigned to conditions, and the measurement scale is at least interval. That is, we're working with quantitative data. That allows us to take the difference between the score we observe with the person in the treatment condition and the score we observe with the person in the control condition. Our null hypothesis is that the median of the different scores is equal to 0. Now, if this is true, and if we swap the control and treatment participant within a pair, the absolute value of the difference in the scores of these two participants will remain the same, but the sign will switch. Here's an example. 12 study participants are matched on extraneous variables into 6 pairs. One member of each pair is randomly chosen to receive the treatment. After the intervention, all participants are measured with higher scores representing a more positive outcome. A difference score, let's say treatment minus control, is calculated for each pair. So because we're looking for higher scores to represent more positive outcomes, then a difference that is a positive number will favor the treatment and a difference that is a negative number will favor the control. Let's suppose we get these 6 differences. The question we are asking is whether this is enough evidence that the treatment was effective. Well, let's consider one of these differences. Let's take that 12, which is a positive value indicating that the person in the treatment condition got a higher score, higher by 12 points. Possibility number 1 is that this participant received a substantial boost from the treatment compared to the control match because the control participant did not receive a treatment. But possibility number 2 is the difference is due to extraneous variables, not the treatment, because the null is true. If possibility number 2 is true, chance is what made the difference between this being a positive 12 instead of a negative 12. Here are the possible sequences of signs that we could obtain with these 6 pairs. We could in fact observe that the treatment participant got a higher score than the control participant, meaning our difference is a plus sign, for all 6 of our pairs. That would be the most compelling evidence that the treatment is working. Or perhaps we find that the treatment participant did better than the control participant in 5 of the pairs. And in one of the pairs, the control participant got a higher score than the treatment participant. If you watched the previous video, you recognize these patterns. But something is different here. Notice that the score I'm using is actually a score, not the number for the individual pairs. So the scores we have, without the sign attached to them, are 1, 2, 3, 6, 7, and 12. Therefore, in that first sequence, we're viewing them as all positive. In the second sequence, we're attaching a negative to the 1, but attaching a positive to everything else. In this manner, I can use this table to represent all the possibilities of randomly assigning pluses and minuses to these scores, which is what we're doing if there is no treatment effect. A big difference here with this randomization test as compared to the randomization test we did with using just signs is we're using the quantity of the observation. So a positive 12 becomes more compelling evidence than, say, a positive 3 when we're looking at the difference between the treatment and control participants. Here are the steps we use to analyze the data from this randomization test. Let T equal the sum of xi positive sign, where xi positive sign is simply going to be the score if that score is greater than 0, and xi positive sign is going to equal 0 if the score is negative. In other words, let T be the sum of our positive scores. An exact test is to place the values of T most incompatible with the null hypothesis in the rejection region. And we're going to establish our rejection region and our critical value such that the probability that the T will end up in the rejection region conditioned on the null hypothesis, that is, the null hypothesis is true, is less than or equal to alpha, our maximum tolerance for a type 1 error. So going back to our example, if all of the scores ended up positive, we would include them all when we were summing up in order to arrive at the value of T, and we would get 31. If the 1 was negative, but everything else was positive, we would end up with 30. If the 2 was negative and everything else was positive, we'd end up with 29, and so on, all the way down to the bottom of the table in which everything is negative, and so when we add up all the positive numbers, we get 0 because there are none. So let's look again at the data that we're using for this example. In this case, we're going to add up 3, 7, 6, and 12. That gives us 28. If you look at the table, we see that 28 can occur 2 different ways. If we want to calculate our p-statistic, we're going to take the 28 that we observed and every value that's even more incompatible with the null hypothesis, that is, higher values of t. Remembering that each of these sequences are equally likely if the null hypothesis is true, so that each sequence has a probability of 1 over 64 of being observed, we can look at the fact that we have 5 values that are 28 or greater, meaning that 5 over 64 or 0.078 is the value of our p-statistic. If I am using a tolerance of 0.05, where would the critical value occur? It would be 29. That is, we would reject the null hypothesis for 29 and above because 3 over 64 is 0.047. That is the closest we can get to 0.05, our tolerance level, without going over. We had a p-value that was greater than 0.05, so we would not reject the null hypothesis. And looking at this a different way, our observed value of 28 is not in the rejection region. What if we said that because we're only using 6 values, we would be justified in using a tolerance for type 1 error of 0.10? Well, in that case, then we're going to look at 27 as our critical value, because the probability of getting 27 or greater is 6 over 64. There are 6 numbers that are 27 or greater, and that gives us 0.094. So if we had used a 10% tolerance for a type 1 error, we would have rejected the null hypothesis with these data, which would have led us to conclude that the treatment is effective. One final note. The parametric alternative to this particular randomization test is the match pair t-test. That is, individuals who use this match pair design and collect quantitative data and who know nothing about nonparametric methods are almost certainly going to use the match pair t-test to make their inferences. We are learning about nonparametric statistics, so now we have an alternative. We actually have 2 alternatives so far, and we're going to learn more. The sign test or this particular randomization test using original scores. Comparing this particular randomization test to the match pair t-test, something interesting happens. As the number of our observations goes up, the p-statistic that we will calculate from the randomization test and the match pair t-test converge, so that with large enough observations, they are going to give us the same p-value. Does this confirm the validity of the randomization test? Actually, it's the other way around. With the randomization test, we are calculating exact values. And if you read the writings of Ronald Fisher, what you will realize is that he would say that this helps verify the validity of the t-test because the p-values for that test converge to those of the randomization test, which gives exact values as the number of observations increase.